Hello and welcome to this presentation, A Connector Manufacturer's Perspective on Form Factors. I thank all the attendants for your interest and in particular the ECOC and the Market Focus team for making this presentation possible despite the Corona lockdown situation. Yamaichi is one of the leading connector manufacturers for pluggables. We vividly contribute to those associations you can see on the slide. As a highlight, I would like to mention that we provided the leading design for CFP2, CFP4, and CFP8, but also for smaller form factors like DSFP and NGSFP. Our portfolio consists of plugs, which are used in some pluggable modules, host connectors, and mechanical parts, such as cages, heatsinks, and clips. Complementary products that influence us are, of course, the pluggable transceiver modules, but also the network equipment, like the network interface cards, switches, OTN devices, etc. Form factors have evolved over time. We would like to share an insight on how we address the challenges like thermal dissipation, data rate, etc. when we design a connector. Secondly, we think pluggable form factors will be replaced by onboard optics and other approaches in the future. Therefore, we, as a connector manufacturer, need to shape our development roadmap in a form that we are future ready. Also here, we would like to share our idea with you. Choosing the right form factor isn't always easy because parameters can create conflicting interests. Backwards compatibility conflicts with data rate, transmit power conflicts with heat dissipation, etc. So, as a first point, we would like to address the point of backwards compatibility. Backwards compatibility is achieved with the double density approach, or DD. You can see there are some form factors that already have been widely accepted by the industry, such as QSFP-DD, SFP-DD, and NGSFP-DD. They are all backwards compatible with the original form factors QSFP, SFP, and NGSFP. For those of you who don't know how the DD approach actually works, you have an old heritage row of contact and you have a new row of contacts, the double density contact rows. So if you use an original form factor, it will just contact with the first row. If you have the double density form factor, it will contact with both rows, the front and the rear row one. The double density approach comes with pros and cons. As the name already says, the density is doubled, which means the amount of channels is doubled. So for QSFP, you have 4 channels. For QSFP-DD, you have 8 channels. That is the huge advantage. On the other side, the DD approach is more vulnerable to crosstalk, and the soldering process is more complex. We think that 112G is very challenging for the double density approach. So with NGSFP, Yamaichi suggested to significantly increase the distance between the first and the second row. And this was possible because we skipped one innovation cycle and designed directly for 112G. If we talk about double density, we should also talk about the density itself. So in this table, you can see we assume that QSFP-DD can have a throughput of 25.6 tera on a standard rack unit. This is achieved with 32 slots. For NGSFP-DD, the amount of slots is actually higher, it is 48. Same as for SFP-DD and DSFP and SFP100. But the total data throughput for NGSFP-DD is still 19.2 tera. For SFP-DD, it is exactly the half of it. and then it gets decreasing. So let us talk about another conflicting interest, about heat dissipation. Of course, a larger surface is always an advantage for a better heat dissipation. Here you can see an example of CFP2 approaches to improve the heat dissipation. A larger surface is always better, of course, but what if you cannot go larger, if you don't have the space? Well, then a heat pipe is a good solution. A heat pipe actually looks like a bare piece of copper, but it is more complex. It is a tube filled with a cooling liquid that circulates. On the hot end, the liquid gets evaporated. On the cold end, it gets condensated and returns as a liquid to the hot spot. This allows a terrific good heat dissipation, in some cases even better than liquid cooling. A not so orthodox approach to improve the heat dissipation is to cut out the PCB. Cutting out the PCB will allow you to gain some height. This height can be used to improve the airflow, for example, or to increase the fins of the heat sinks. Or, as a last option, you can simply reduce the height of your housing and realize a half-size rack unit OTN device equipped with CFP, which is quite flat and compact if you think about it. So, one question that is maybe not so obvious is, what about optimizing old form factors instead of using a new one? New form factors come with new features, but they also come with an additional design-in activity. If you go from QSFP to QSFP-DD, the foot pattern changes. Also, the size of the cage changes. So a legitimate question would be, why not keeping the old form factor and just upgrade it? CFP has been upgraded from 10G to 112G, allowing more than 1 tera of throughput. QSFP has been upgraded from 28G to 112G. This is actually a 400G form factor. I'm not talking about QSFP-DD here, I'm talking about QSFP 112G, which has the same throughput per slot as QSFP-DD 56G. Last but not least, also CFP2 has been upgraded to 112G, but not only the data rate, but also the wattage. Originally, we had something like 10 watts that we could use on a CFP module. Now we can go beyond 24 watts, and this is really important for coherent transmission. The key takeaway here that we would like to share with you is that you have two options. When you have a new project, you can design in a new form factor, or you can keep the old form factor and optimize it. Now, what about alternatives to pluggables? As I said, the future might bring some approaches that will replace or partially replace pluggables. Here we can see an example of different scenarios. The top scenario is the current one, where we use a cage, a connector, and a pluggable that is plugged into that connector. But all other approaches are thinkable. We have embedded optical modules who don't require a pluggable connector anymore. Or going even further, we can see that optoelectrical interfaces are embedded on multi-chip modules and so on. So the problem with optoelectrical interfaces embedded on a PCB or on a multi-chip module is that they are sensitive to heat and in many cases cannot undergo the SMT reflow. Therefore, we install a socket. A socket can go through the reflow process and then the heat-sensitive device is plugged onto that socket on a later assembly stage. The required specification for such sockets would be, of course, 112G compatibility. detachable, solder or compression mount, and from a multiple of 100 pins to a multiple of 1,000 pins. Here on that picture, we can see a multi-chip module that is equipped with multiple chips. The switch, for example, could be placed on a socket consisting of 1,000 or 2,000 pins. The small IC or SerDes here could be considered to be plugged on a socket of a couple of 100 pins. And the entire multi-chip module also could be attached to a PCB with a socket of several thousand pins, 5,000 pins, or even beyond that. If you have any questions about this presentation, please don't hesitate to contact me. If you have questions about Yamaichi products, please contact your closest Yamaichi sales office. Thank you very much for your attention.